Hi, my name is Bensman. I'm going to be going over our group's project here for today. So, as you can see, for our group's project, we made a bridge. Well, we actually made a model of a bridge. It's a truss bridge, not just any truss bridge. It is the Salmon Falls Bridge, which is located in California, right outside of Sacramento. And like any useful bridge, it goes over in order to talk about the material selection process, different metal processing techniques, and general mechanical properties. So the bridges of the olden days were often made out of wood and or stone, but more modern bridges incorporate a lot of steel, concrete still, and then the newest on the block is fiber reinforced polymers. Those haven't made it big yet, but we'll see. So the general material selection process, it goes like this. So step one is to pick your application, and then off your application you can figure out what kind of material properties are desirable. And then once you have those properties, you can propose possible materials, and then once you have your material, you can look at different processes to get the exact properties that you would like in that material. So we're going to walk through that with our bridge. So step one, we have to pick our application. We're going to be building our truss bridge, and our desired properties there would be strength for sure, but also ductility. In a truss bridge, your members have to endure both tension and compression. We also want to think about longevity of the bridge. We don't want our material to degrade quickly. We prefer it to be lightweight, and as always when you're building something, you have to consider cost. So step two, once we've proposed some of those properties, we're going to look at some different materials. In this case, we're going to be looking at metal, wood, and polymers because of their general properties. Let's start with metals. The positives, they're very strong as a class of material. They're generally ductile, and that they have a high strength to weight ratio. They can also take both tension and compression in most instances. However, they can be expensive, especially depending on the process that you put them through, and they are prone to rust and then eventually cracking if they're not maintained properly. Wood is strong, but it's not nearly as strong as our metals. It is very lightweight, and it can be pretty cheap. However, it can also be brittle, and then it is prone to rotting, which if wood rots to a certain extent, its mechanical properties are almost completely negated. So then moving on, we'll go to polymers. Polymers have some really good qualities about them. They're lightweight, they're very cheap, resilient, and ductile. But they are very weak. So they won't be super great in an application like a large truss bridge. So we're going to select metal. More specifically, we're going to be looking at steel. It's taken over, especially in the bridge building world. It used to be just iron, but with the addition of a little bit of carbon, we can create a much stronger metal. And then the process that we're going to put these through. So our bridge has many members to it, a lot of different components, but it's also almost entirely made out of steel. But those different components will have different processes depending on the properties we want out of each one of those members. So as we're going over the plans, the original blueprints to our bridge, our Salmon Falls Bridge, we found that there was 4 main types of steel used in the bridge. One for the big I-beams, then we had different ones for the rivets, different ones for this and that in the bridge. So it can get fairly complicated and specific. So moving on then, we're going to look at some of the processes that are commonly used in processing steel. This will be cold working, and that's often used along with annealing. And we've got hot rolling, and then the process that creates some of the highest strength steel is quenching and tempering. But let's start with cold working. So what you see here is a piece of steel, and this diagram shows its grain structure. It's going through two big rollers that are reducing its diameter down. And this is all done at room temperature, but by doing this, we are stretching out these grains and elongating them. This elongated grain structure has a higher strength, and which is more favorable in certain applications. But this process often creates stresses throughout the material, so it is often done along with annealing. You put it through the cold working process, and then in the annealing process, that metal is heated back up, and that heat will alleviate some of the stresses. It's allowed to cool very slowly, and so it creates a more uniform piece of metal with a more uniform mechanical properties. So then we've got hot rolling, which is essentially the same thing, but it's done at a very high temperature. We still have the grain structure here, but by heating it up, we basically normalize the steel or turn it back into the austenite phase. So then we can run it through the rollers and elongate that grain structure, but then we can cool it down, and we'll have a uniform piece of steel with uniform mechanical properties without having to go through the annealing process afterwards. We've then got the quench and tempering process. Basically, it goes like this: you heat it up, you quench the metal, and then you heat it back up again. So we're going to look at the grain structure throughout this process. So this diagram depicts just plain old carbon steel before it has been processed. We're going to heat the piece of steel up. The austenite phase will kind of take over the piece of metal, and it'll come out from these grain boundaries and continue to grow until it is completely taken over the piece of metal. And then we're going to quench that piece of metal very rapidly, usually in a large pool of water. By doing this, we make this needle-like structure in our steel, which is extremely strong, but it is also very brittle, and the brittleness is not very desirable. So we're going to heat our piece of steel back up, and then let it cool slower this time, and then we'll get carbon within these needles, and basically this will restore some of the ductility and reduce the brittleness of that steel, keeping it very strong, but reducing the brittleness of the material. So then finally, let's move on to some of the mechanical properties that we see in different materials. This being strength, ductility, malleability, hardness, toughness, plasticity, and elasticity. Depending on our application and what engineers are trying to build, we're going to be looking at different properties, and some are valuable in certain applications, and others not so much. A common way to look at some of these material properties is on a stress-strain graph. So let's go back to steel. As we can see, we've got strain on our horizontal axis and stress on our vertical. Then we've got this funky line here. This linear region right here is the elastic range, which basically just means you can put any force on it, and then it will still bounce back to its original shape after that force is let go. But then if you push that same piece of metal past this point, which is its yield strength, it'll start to plastically deform, which means that when you let that force go, it will not bounce back to its original shape. And this is where you enter the strain hardening region, which is what we were doing when we were going through the cold working process earlier. We're basically pushing it past this yield point, and anything that you leave in this region and let it go, it will increase the mechanical properties of that piece of metal. And then at the top here, we've got our ultimate strength, which is what it sounds like. It is the highest strength that piece of steel will have. And then if you go beyond this, a neck will form and it eventually will fracture. And this is not something that we want to get to when we are building a bridge. Here are some comparisons of yield strength. I pulled this image from Raleigh Green's Chapter 6 lecture. As we can see, metals generally have a higher yield strength than our other materials. Steel being at the top, and that is the quench and tempering technique. It is quite a bit larger than the rest of our yield strengths here, but we can still see steels through different processes still have very high yield points. This is one of the reasons that it makes it a great material to build some bridges out of. So what have we learned? We have learned that material science is cool. In order to make anything, we walked through it with a bridge, but in order to, design anything effective, you have to know what materials you're using and how they behave. If any engineer is ever going to build anything useful, it's best that they know a little bit about material properties at least, or else it is very hard to build anything. So just to wrap up, we're going to be looking at a couple bridges that didn't fare so well, and either they were designed poorly or their materials just didn't hold up. So first, we've got back in the 1800s. This was a bridge in England. They had a train going over the top of it, and as you can see, it failed and the train fell into the water. Similar thing happened here. These cross members here were made out of iron. It couldn't support the weight of the bridge, and it fell right through the bottom. This is the San Francisco Bay Bridge. This actually happened in an earthquake, but same thing. The steel gave way there and just flopped right down on top of the section below it. And finally, this was a bridge over the Mississippi River. It had an increased load due to some construction, but it was also maintained poorly, and one day during rush hour, it just collapsed on us. So that was a pretty big tragedy, something that engineers want to avoid, and knowing material science is a way to do that. So that's all I've got for you, but thank you for your time. I hope you found this valuable.